Alright, hi guys. This is the Intermolecular Forces, or IMF video, and we're going to talk about intermolecular forces, how structure affects intermolecular forces, and how intermolecular forces affect the properties, the state of matter, the vapor pressure, the boiling point, all of that. That's all linked back down into the structure of an atom. Alright, everything, intermolecular forces, is based on the structure of a molecule. I'm sorry, I said atom before, but it's a molecule. Alright, so everything is based off the structure of a molecule. Alright, these atoms don't have inherent wants or needs. Water doesn't want to stick together. It's because the molecule is shaped a certain way, it exhibits certain intermolecular forces, and those intermolecular forces are held together through electrostatic or magnetic bonds, essentially. Okay, so it all comes back down to the structure of the molecule. The structure of the molecule is incredibly important when we're talking about the properties of it. Okay, so let's get started. When we're talking about the structure, one of the most important things we need to remember is symmetry. Alright, is symmetry. Symmetrical molecules, like, for example, CH4. Alright, CH4 is symmetrical, meaning it's the same top and bottom or left and right. It's a symmetrical atom. Now, it's not going to share its electrons equally though. Carbon is more electronegative. That means it has a partial negative charge on my carbon. And my hydrogens have a partial positive charge. So there is a dipole present. Right? There's a dipole, there's an unequal sharing of electrons. But the reason why it's not polar is because if I have another CH4 or methane molecule come next to it, the only part of the methane molecules that can bump together are the partial positives. Right? There is no way for that H to get past these partial positive charges. It creates almost like a positive shield around it. It creates almost like a this partial positive shield, and there's no way for these molecules to interact. That means that there's no interactions between these molecules. In fact, there might even be a repulsion on a very small scale between these molecules. So symmetrical molecules have no dipoles. And by that, I mean no polarity. Okay? Dipoles is an unequal sharing of electrons. Polarity is the actual intermolecular force. Okay, so symmetrical molecules have no dipoles, and therefore they have no polarity. Asymmetrical molecules do, though. Asymmetry. Let's say, for example, with asymmetry, we have a molecule like HCN. Alright, I have HCN. This is clearly not a symmetrical molecule, right? The left side of this molecule is different than the right side of it. It's asymmetrical. Nitrogen is the most electronegative, so it's going to have a negative charge. And hydrogen is going to have the partial positive charge. What this means is, let's say we have another HCN molecule. Let's draw it right here. I've got the space for it, why not? That means that now this partial positive and this partial negative can interact. It's a force between molecules. Intermolecular means between molecules. Alright? Intermolecular. Between molecules. So I have a force between two molecules. This is called polarity. It's also called hydrogen bonding when I have a hydrogen involved. Right? Tiny Tim is really excited right now. He loves hydrogen bonding because this type of bond is responsible for holding a lot of biological things together. Like the two sides of a DNA molecule, the double helix, is held together with hydrogen bonding. Water molecules are held together with hydrogen bonding. It's one of the most popular types of polarity. Okay? So because I have a difference in charges, I can have an intermolecular force when it's asymmetrical. So asymmetrical molecules have polarity. Right? They will have a polarity. Okay. Now that leads me to one other type of force. We're talking about polarity. We talked about hydrogen bonding, which is essentially polarity, but with hydrogen. Last but not least, we have something called London dispersion forces. Okay, London dispersion forces are kind of odd. London dispersion forces occur in large molecules. They occur in large molecules. And it's kind of like a clumping of electrons. It's a clumping of electrons. Now, what I mean by that is, let's say we have an iodine molecule. All right, it's diatomic, so there's two of them. And iodine has about 106 electrons. It has exactly 106 electrons, actually. Now that means that those electrons are in multiple energy levels. I drew this horribly. They're in multiple energy levels. And all 106, since it's completely nonpolar and there's no dipole at all because they share electrons equally, those 106 electrons are going to be whizzing around both molecules. Okay? It's going to be creating almost like this large cloud around both of them, large electron cloud around both of them. And just like anything, since it's randomly distributed, there will be times where I have a higher concentration of electrons in one area and a lower concentration somewhere else. Let's say I have a high concentration of electrons right here. Let's say I have a high concentration of electrons. What that means is I'm going to get a partial negative charge there because I have a lot of electrons. Subsequently, I'm going to have a partial positive charge here because if there are a lot of electrons here, it means there aren't many electrons there. You can see that this is going to cause a slight polarity, or it's going to cause a slight intermolecular force because I have more electrons here than I have here. It's the same exact thing as our other molecule. Right? Here I have more electrons because it's more electronegative, and here I have less because it's less electronegative. Right? Here I have more because they clump together, and here I have less because they didn't clump together. Now, this is, I'll admit, a tenutive property, meaning that it kind of comes and goes. But if I have a lot of iodine together, and since it's a solid, they would be packed pretty closely together. And I will draw 3 iodine molecules. If I have a slight positive charge here, that's going to induce a London dispersion force over here, which will cause a London dispersion force over here, which will induce another one. So you can see this chain reaction, whereas when one starts, it makes every other one kind of go. And they kind of reinforce each other, because now it's going to be trickier for this molecule to not clump up, because this one is helping stabilize it. So there are some stability factors there. Okay? Now it's important to remember that these are intermolecular forces. All right, I'm going to erase all of these. These are intermolecular forces. And they are not the same thing as bonds. Intermolecular forces are weaker. They are also longer. So they're forces interacting between the two molecules, but they're not the same thing as two molecules bonded together. They are inherently weaker because they're partial charges. It's not a sharing of electrons. It's not a full charge like an ionic. It's a partial charge. And also, they are longer because they are weaker. All right, they're not overlapping electron clouds. They're 2 electron clouds interacting with each other. When I have a molecule bonded, let's say it's a single bond. Oops, that did not work at all. If it's a single bond, there we go. Those electron clouds have to overlap for those electrons to be shared. If I have an electron coming in here, it's got to overlap for it to be shared between my 2 molecules. In an intermolecular force, though, they don't overlap. It's the 2 clouds interacting, but at a little bit of a distance. It's like me and Tiny, right? We interact at a little bit of a distance. You know, I don't like to associate with them too much. All right? We interact at a distance. We don't overlap. So it's inherently weaker. All right? Now let's talk about one other thing. Before I talk about the effects of intermolecular forces, I want to talk about Coulomb. Coulomb. Ooh, I hope I spelled that correctly. Let me double check. Yeah, of course I have no idea if that's spelled correctly, so we're going to go with it. If you're that concerned, you can just Google it. The Coulomb forces. Let's say, let me define it first. Let's call it the strength of the attraction, or the strength of the intermolecular force. Okay? Let's say I have two molecules. I have molecule X and I have molecule Y. Okay? Or atom X and atom Y. Let's say they have equal forces. So they both exhibit the exact same amount of dipole, the exact same amount of London dispersion, the exact same amount of polarity, or very similar amounts. Maybe they're not exact, but they're very, very similar. So I have two molecules, X and Y, and they have almost equal intermolecular forces. Let me write that. Intermolecular forces. Now let's say, however, that X is smaller than Y. The atom itself is physically smaller. So it could be something like neon and helium, or sodium and potassium. They are physically smaller atoms. If X is smaller than Y, X will exert a stronger pull towards other atoms. Okay, let me bullet point these. X will exert a stronger pull because it's smaller. Think about it. If I have molecule X and I have a bigger molecule Y, and let's say the force is 10. Okay? So the force, whatever 10 is. Okay? Let's say the radius of X is 1, and let's say the radius of Y is 10. Okay? So they both exert the same force, which is 10. Or they both have the same force, I should say. They both have the same force. But X is smaller than Y. That means that the force of X is less spread out. Meaning that it's more concentrated. It's able to exert the force stronger because it's small. Whereas Y's force is spread out. It's diffused. It's harder for it to kind of grasp things because it's bigger. It's kind of the principle of ionization energy. Because it's bigger, it ionizes easier. It's harder to exert that force. It's called a Coulomb force. It's called a Coulomb force, or the Coulomb forces. The Coulomb principle is that the smaller the atom, the stronger the force it can exert. So if I have two equal forces, the smaller atom will exert more force. Okay? Or a more concentrated force, I should say. Okay? I have one last thing. I'm sorry. I thought we were done. We're not. This is like the song that never ends. It's awesome. Okay. Let's do blue. I don't know why I'm holding 1,000 of those things. All right. Let's do the effects of intermolecular forces. Okay? Now think of intermolecular forces, or atoms with intermolecular forces. I'm sorry, I keep saying atoms. It's molecules. I don't know why I do that. Let's say molecules with intermolecular forces are like Velcro. Meaning they stick to each other. They stick to each other. They don't like to be apart from each other. The water molecules stick to each other. That means if they stick to each other, they don't fly away. They won't fly away from each other. Now, I, and the rest of the science world and the world in general, like to consider molecules that fly away evaporation. Since they're stuck to each other like Velcro, it's harder for a molecule to fly away, to evaporate, to turn into a gas and leave. All right? So they don't fly away, they don't evaporate. What that means, if they don't fly away, they have very low vapor pressure. They have very, very low vapor pressures. All right? They will not fly away. And we've talked about vapor pressure in class, but it's the pressure of a vapor. All right? A beaker of water, and I don't have water, that's why I was looking around, but a beaker of water has a low vapor pressure because the H2O molecules are stuck together. Okay? And if it has a high vapor pressure, of course the lights went out halfway through the video. I'm not going to stop it though, I'm just going to turn the lights back on. They're motion sensitive, it's kind of fun. Keeps me guessing, but I am way too lazy to reshoot this, so I'm just going to keep going and pretend it never happened. All right? A low vapor pressure means that the water doesn't boil, or the substance doesn't boil. Low vapor pressure is the same thing as a high boiling point. Right? Low vapor pressure means there's not a lot of vapor, so it doesn't boil. Whereas molecules without, or molecules with no or weak intermolecular forces, they fly away. That CH4 molecule that we talked about earlier, there's nothing holding them together, so one just flies away from each other. They spontaneously fly away. Why wouldn't they? Molecules don't really want to be next to each other. I mean, there's even, we talked about maybe a slight repulsion between those molecules. So they fly away from each other. They evaporate. CH4 is methane gas. It's a gas at room temperature because they fly away from each other. They have a high vapor pressure. Meaning at room temperature, there's a lot of vapor. There's a lot of pressure. And since there's a lot of vapor and a lot of pressure, they probably have a very low boiling point. Because they may boil at negative 100 degrees. All right, we're talking about gases like carbon dioxide or things like that. They may boil at very low temperatures. Okay? So that is intermolecular forces. I know it's a long video. I apologize. I'm sorry the lights went off. But, you know, it adds ambiance to the video. All right, thank you very much.